Welcome students. In this class we will be studying the preliminaries of groups. Just a basic idea what the groups are. What kind of structure do groups have? You are already familiar with the various number systems, the set of all natural numbers, integers, set of rational numbers, irrational numbers and real numbers. So this is a slide just to recapitulate that. And before I proceed to define groups, I would just like to recapitulate binary operations which you have already done in your lower classes. You all know that a binary operation is simply a rule for combining two values to create a new values. That is, a binary operation on a non-empty set is a function. We may denote it by naught, star, f, anything we want, from s cross s to s, and it is denoted by a naught b. That is, you have two values x and y. You operate it using that operation naught and you get a new value x naught y. If this new value x naught y is in itself in the set S, then this is a binary operation on the set S, otherwise it is not. So naught, a naught b, naught will be a binary operation if a naught b is the unique element of S for all a and b belonging to S. For every a and b in S, a naught b is also a unique element of the set S. In that case, naught is said to be a binary operation on the set S, otherwise it is not. For example, as we combine two natural numbers using the operation of, say, addition, you add two natural numbers. The result is again a natural number, so addition on the set of natural numbers is a binary operation. Likewise, multiplication. When you multiply two natural numbers, you again get a natural number. 3 into 4, 12 is a natural number. 3 into 5, 15 is the natural number, and so on. So multiplication is also a binary operation on the set of natural numbers n. But what about subtraction? What about subtraction? If you subtract two natural numbers, is the result always a natural number? No, it is not. It may not be. For example, 3 minus 4 minus 1 is not a natural number. It does not belong to the set of natural numbers, as natural numbers start from 1, 2, 3 and so on. So 3 minus 4 does not belong to n, whereas 3 and 4 both were natural numbers. So the subtraction on the set of natural numbers is not a binary operation. So this was just a recap of the definition of binary operation. Let us now proceed to go on to do the definition of groups. So, algebraic structure. A non-empty set S together with a binary operation, one or more binary operation, is called algebraic system or an algebraic structure, right? S, a non-empty set S together with one or more binary operations, is said to be an algebraic structure or algebraic system. For example, the set of reals with the binary operation of addition and multiplication, the set of natural numbers with the binary operation of addition, these are all algebraic structures. So let's now proceed to do the definition of group. Group is an algebraic system G star, that is a non-empty set G together with a binary operation star, is called a group if it satisfies the following axioms. Now what are those axioms? Let us see. First is closure axioms. This is nothing but just to say that star is a binary operation. In other words, we are just enforcing that star is a binary operation, right? So closure axiom, this is just to check if star is a binary operation. That is, a star b belongs to S for all a and b belonging to S. For any two elements a and b of S, a star b is also in S, a unique element of S. Secondly, associative law should hold in S. Associative law we all know, that is, for all a, b and c belonging to S, a star b star c should be equal to a star b star c. That is, the positioning of these brackets is immaterial. You may position it here or you may position it here. The result is not going to change. That is, the associative law should hold, right? Then, very important, the next law is existence of identity. Now, what do we mean by this? Identity, right? Identity means the identity should not change. So that means for every A belonging to G, for every element A belonging to G, there should exist an E belonging to G such that A star E should be equal to A, should be E star A. That is, when any element A is operated with E, the result does not change. The identity of A does not change. It remains the same. A star E is A as well as E star A is A. So such an element E is said to be the identity of the group. And next is existence of inverse. That is, for every A belonging to G, there should be another element. There should exist another element B in G, B belonging to G, such that A star B should be equal to E, should be equal to B star A. And such an element is called inverse of A. And this should exist for every element A belonging to G and is called inverse of A. Right? So if these four axioms are satisfied in a set G under this operation star, this may be any operation, this may be defined in the question depending upon the elements G has, then G is called a group. This algebraic structure G is called a group. And further, if in addition to these four axioms, another axiom, one more axiom is satisfied, that is A star B should be B star A, that is order of operating the elements, whether you operate A star B or B star A, is immaterial, the result is same, then we say that the group is commutative or abelian. The another name for commutative group is abelian group. Then is semigroup. Now what is a semigroup? If in the algebraic system G star, associative law holds, star is a binary operation and it is associative also, then we say it is a semigroup. Okay. In this case, there is no need to check the existence of identity or existence of inverse. Just the associative law, if it is holding, it will be a semigroup. Okay? Or if G, the set G which we are taking is finite, then the group will be finite group. And if the set G which we are taking is infinite, then it will be a infinite group. And the number of elements in this set G is called the order of the group. As we usually define the order of a set, the number of elements in the set, likewise in case of group also, the number of elements in this non-empty set G will be defined as the order of group. Agar G में finite number of elements hai, then G is a finite group, and if G has infinite number of elements, it is an infinite group. So the number of distinct elements in G is the order of the group. Let us now do one example to make the things clear. For example, in this we have to prove that the set of integers forms an infinite abelian group under the addition of integers. Under addition of integers means the operation we are now taking is binary operation we are now taking is addition, and the set, the non-empty set what we are taking is the group of, the set of integers, right? So first let us check, is this operation a binary operation? Yes. We know that when we add two integers, the result is again an integer. So this operation of addition is a binary operation on the set of integers, that is Z. We denote integers by Z. So for all AB belonging to Z, A plus B is a unique integer. That is, A plus B also belongs to Z. So star is a binary composition on Z, or in other words we say that Z is closed under star. This is the first axiom. Also we have been doing from our lower classes that addition is associative in integers. Whenever we add from first two elements and then add third, or first add the last two elements and then add first, the result does not change for addition. So the associative law also holds also. Now moving on to the third axiom. We know there is a number 0 in integers which we add to any element, the result will not change. A plus 0 will be A is equal to 0 plus A for every A belonging to Z. So 0, the element 0 is the additive identity in Z. Existence of identity is also done for integers. And last axiom was what? The existence of inverse. एग्जिस्टेंस ऑफ इन्वर्स के लिए हमें क्या चेक करना है? इसके लिए हमें ये चेक करना है कि ए में मैं क्या ऐड करूं सो दैट आई गेट द आइडेंटिटी एलिमेंट. व्हाट इज आइडेंटिटी? आइडेंटिटी इज 0. So obviously for every a, if I add minus a to it, I will get 0. And for every a, minus a will also be an integer. So for every a belonging to z, minus a exists belonging to the same set of integers such that a when added to minus a gives me 0. So minus a is additive inverse of a. Moreover, the order does not matter. I may add in any order. A plus b is equal to b plus a for all ab belonging to z. So this is a abelian group. Commutative law also holds. This is a commutative or abelian group under addition. So z plus, this algebraic structure z plus is an infinite abelian group. So I hope this definition of groups is clear to you. So next, now you have to check on your own. What do you think about n plus, the set of natural numbers under addition? Is this a group? If yes, why? And if not, why not? So this is a question for you to think over, which we will discuss in the next lecture. That is n plus a group or not? You may also comment if you want, right? So happy learning. Read it carefully and understand it carefully. Any questions we'll take up in the class.